So we're going to be looking at Newton's universal law of gravitation today. When you take a look at the title of this unit that we're in, it's called Dynamics and Gravitation. So we're going to do gravitation now. Dynamics was a lot more extensive than gravitation. We have 4 lessons that we're going to deal with on gravitation this week, which means on Friday of this week and Monday of next week we will be reviewing, and your unit exam is tentatively scheduled for Tuesday of next week, but it might be Wednesday. We'll see. I might want to squeak in another lab or some more review. Anyway, we're going to be applying Newton's universal law of gravitation today. I want to review something, though, that is not in your handout, and it's the idea of a proportionality. That when we talk in math about y being proportional to x, this is very important, and it's very closely connected to the graphical analysis for your last lab that we did. In fact, it's exactly the same kind of idea. But it's going to get more complicated with Newton's universal law of gravitation. What does it mean when I say y is proportional to x? Well, that little kind of fishy shape is a proportionality symbol. And what it means, basically, graphically, is this. That's what it means. It means that in a perfect world, if y is proportional to x, when y is 0, x is 0, and it goes up with a constant slope. An example of 2 things that would be proportional would be the cost in dollars and the number of liters of gas I put in my tank. Okay? That would be a proportionality. And I want you to notice that if I were to put, say, 10 liters in my tank, I would get a particular cost. But if I were to put 20 in, because it's a straight line, I'm going to get twice the cost. The concept of a proportionality, if we walk away from the graph for a minute, is that if one of the quantities doubles, so does the other. If one of the quantities triples, so does the other. If one of the quantities is cut into a third, so is the other. And there's many examples of proportionalities out there, but this number of liters and cost, I think, is pretty straightforward because we understand there's a relationship between the number of liters and the cost. Well, what is the relationship? We'll get back to the gas example in a second, but the relationship is that y equals some number times x. I mean, let me make a table of values here, and this is really important. You might go, well, this is turning into a math lesson. I know it is, but it's embedded within the physics. If I had number of liters, we'll say this is in liters, and cost, this is in dollars, and I'm not going to pick weird prices per liter, okay? And, of course, we know if you pull up to the tank, you go, oh, man, I forgot my wallet at home. You turn around, you leave, the cost is nothing. I pump 10 liters, and I don't have a lot of money, so I only pump 10 liters. Or maybe I don't realize, but my tank is almost full, and that's all it will hold. It's $18. I think you can figure out here how much it would be for 20 liters. I don't think that's a difficult mathematical problem. What would it be, Nate? You can use your calculator if you like. 36. Okay, I mean, you pump twice as much gas, it's 36. And if I had 30 liters, I'm not going to double it this time, but what I'm going to say is it's going to go up by another 18. And this is another way, is that 54? Is that right? This is another way you can identify proportionality, is that my x is going up by the same amount each time, and my y goes up by the same amount each time. I'm not saying y is going up by the same amount x is going up by. I'm just saying it's going up by the same amount each time. Well, if I said to you that means that the cost is proportional to the number of liters. That makes sense, doesn't it? It would look like that. What's the equation? I'm asking everybody, what would you do to the number of liters here to get the cost? In all of these cases, what would you do? I'd like you to figure out the answer to that question. Alex, have you got it? So that means the cost is 1.8 times x. Well, look at what I'm saying here. Y is proportional to x. Cost is proportional to n. That means y equals some constant times x. Well, cost equals 1.8 times x. 1.8 is the number here because the gas is $1.80 per liter. That's what it means. It has a significance. But I also want you to notice something, that if I put here this point, which is 10, 18, and this point, which is 30, 54, and I use those 2 points to find the slope of that line, I'll get 1.8. Because it's gone up $36 and it's gone up 20 liters, so your rise is 36, your run is 20. Oh, this constant, which we call in science a constant of proportionality, is actually the slope. In fact, I hope you recognize y equals mx as a math equation. Yes? Okay. Whenever you have a straight line graph that goes through the origin, the equation of that graph is y equals the slope times x. That is why in our lab, when you plotted the force of friction here and the normal force here, that the slope was equal to mu, because the force of friction equals mu times the normal force. The cost of gas equals the cost per liter times the number of liters. So the cost per liter is the slope. So that's a very quick review of what we call a direct proportionality. Now let's look at the problem of universal gravitation. It turns out, and this is a hard thing to imagine, that anything with mass is attracted to anything else with mass. My head is attracted to the moon. Your calculator is attracted to your phone. But for small masses, the force of gravity, which is that force of attraction that I'm talking about, is very, very small. Gravity usually only reveals itself to us when you're talking about large masses. And the problem of universal gravitation is basically if you have two masses, and I'm guessing that yours says m1 on the left and m2 on the right, it doesn't matter the order of them. It turns out that any two masses are attracted to each other, and the amount of attraction depends on how far apart they are. I'm sorry, we use r for the distance between them. And it's because later on in the course we'll want to equate that to what's called the radius of a planet, or the radius of orbit. Okay? M1 is one mass and M2 is the other mass. And Isaac Newton thought about this. This is the story, I don't know if it's true or not, it's debatable whether it's an actual true story, of an apple falling from the tree and hitting him on the head, and him wondering why the apple fell. I think that's more a fairy tale version of what was going on in his mind. But he knew that objects were attracted to the earth, and he wanted to figure out what the explanation was for that force of attraction, or how that force of attraction was related to things. So in what I have up here, M1 might be the apple and M2 might be the earth. Are you with me on that? Okay. What Isaac Newton hypothesized, and you're going to study something in Physics 30 called Coulomb's Law, which is so similar to this. What Isaac Newton hypothesized or proposed were the following ideas. He thought that the force of gravity was proportional to the product of the masses. I want to explain what that means. If the force of gravity is proportional to the product of the masses, that means if the masses are doubled, the force doubles. It's a little more nuanced than that because there's two things here. So what this means is, let's just imagine that you have M1 and M2. And these have certain values, we don't care. And the force due to gravity between them is 100 newtons. So right away, I know that you're used to thinking of force of gravity as weight, okay? But now we have to wrap our heads around this. The force due to gravity is the force pulling these two masses together. And let's just say it's 100 newtons. Okay? The question becomes, what if I double this mass and I triple this mass? So the new mass will be 2 times the old mass and 3 times the old mass. What will the new force of gravity be? I'm going to give you a second to see if you can figure it out. What do you think the new force of gravity is going to be? Put your hand up and then down if you think you know. So a question for you. Is it the fact that there's two variables there, m and m, that is causing you to think about this a little bit more? So how many of you think you know now? Still the same people. Well, I'm going to put somebody on the spot here. Nate, what do you think? Well, if you guess, nothing bad's going to happen. The universe isn't going to fold in on itself. And I mean, you're not going to guess like throw a dart at a board or anything, but we've said that proportionalities mean as one goes up, the other goes up. So will the force be greater if we have more mass? Okay. What do you think it might be? Right. So what do you think? If it was 100 newtons to begin with, well, how many newtons do you think it's going to be now? Don't even want to guess. Gabrielle, what do you think? Pardon me? It's actually not 100 newtons because the force is proportional to the mass. So the amount of money that I pay at the pump is proportional to the number of liters. So if I pump more gas, I pay more money. It's got to change. Aoki? Can you repeat that? That's right, 600 newtons. Is that what you thought, Jay? Alex? Go back to what I said about the gas, and I think I even have some numbers up here we can look at. If I go from 10 to 30, I've multiplied that variable by 3, and what's happened to the cost? It's gone from 18 to 58, which is multiplied by 3. The difference here is there's two things. One of these is doubled, one of these is tripled. But if this is proportional to both, when I double one of the masses, the force is going to get doubled as well. If I triple the other mass, it's going to get tripled as well. Another way to look at it is, if I double this first mass and I double or triple the second mass, then this whole thing gets multiplied by 6, doesn't it? If that gets multiplied by 6, the force gets multiplied by 6. So this is what we mean, or what Isaac Newton means, when he feels that the force is proportional to the product of the masses. Let's just let that settle in, because it's going to get a little more complicated in a second. What Isaac Newton believes is, when you have these two masses, that the force pulling them together, this force of gravity, depends on the masses in such a way that if you have a bigger mass, you have a bigger force, basically. Okay? And by the way, and we would never be able to do this experiment here, but if you get a chance to look at an experiment testing this force of attraction in university, it's amazing. They take 2 lead balls and they hang them on a balance by a very thin wire, and they bring a third lead ball close to one of them, and the whole thing moves. You're able to pull that lead mass towards the second lead mass with the force of gravity. We're so accustomed to thinking of gravity as being this thing that is sticking us to the earth, and that is true. But it exists between any masses. Now comes the second part of his proposal, that the force of gravity is inversely proportional to the square of the distance. Okay, what does this mean? It means a lot of things. First of all, the fact that it's 1 over means this. As the distance gets bigger, the force gets smaller. Okay, so what this means over here is, if m1 goes up, the force due to gravity goes up. If m2 goes up, the force due to gravity goes up. If m1 goes down, the force of gravity goes down. Whatever happens to either of the masses happens to the force. What this means is, if r goes up, remember, r is the distance between the objects, the force of gravity goes down. And I think, even though gravity, and I understand this is difficult because you don't think of gravity this way. You think of gravity as being something that pulls you to the earth. It's bigger than that. There's something else going on here. But I think intuitively that kind of makes sense, that if I tell you these two masses that we're talking about are pulled together, that if they were further apart, they would be pulled together less. And it may not be the kind of thing where you could explain why, but there's something going on between the two masses that we won't even talk about in this course, but we do in Physics 30. There's something going on that's causing them to come together. There's something connecting them, weirdly enough. So if they're further apart, that connection must be less. It's like a weaker signal, maybe, is a way to think of it. But this squared really messes things up. So let's take a look at some situations here, and then we've got examples as well. What if m1 was multiplied by 5? What would happen to the force of gravity? You okay? It would also be multiplied by 5 because they're directly proportional to each other. If m2 were divided by 6, what would happen to the force of gravity? Also divided by 6. A direct proportionality, and by the way, these two things can be happening at the same time or two different situations. Don't worry about it. A direct proportionality, which is what we have here, means whatever happens to one happens to the other. Whatever happens to the mass happens to the force. An inverse proportionality means, well, if r is multiplied by 2, what do you think is going to happen to the force? And actually, you know what? I'm going to start with if r is multiplied by 3. What do you think is going to happen to the force? And I will warn you that you might be wrong. Divided by 3 is wrong, but it's close. Anybody want to add something to that? You think you got it? No. It's still divided by 3, not negative, but there's something else. And it has to do with what's written right above here, Jay. It's divided by 3 squared. So what this is saying is that the force of gravity is proportional to 1 over this. So whatever happens to r happens to the force and happens to the force. So what happens here is the force due to gravity is divided by 3 squared. So here's the inverse part. The inverse part is this. I don't like the word inverse, but for some reason it's stuck in science over the centuries. Opposite is a better word. Okay. I guess inverse is fine. It just has different meanings in mathematics, and that doesn't really apply here. So if you multiply r by something, you divide the force by that same number. But the squared part comes in because we have the r squared, so we're dividing not by 3, we're dividing by 3 squared. So what do you think would happen then if we divided the distance by 2? That means you're going to take the two objects and move them half as close. What do you think would happen to the force? Alex? Multiply by 2 squared. So we didn't actually say what 3 squared was. 3 squared is 9. When you triple the distance, the force becomes 1/9 as weak. When you divide the distance by 2, the force gets twice as strong. Squared, 4 times then. So we still haven't gotten into any examples or what Newton's universal law of gravitation is. But this is essentially what it boils down to then. If you take those two proportionalities and put them together, this is what Isaac Newton, napping under the apple tree, thinks is going on in the universe. That the force due to gravity, say, between the moon and the earth, is proportional to the product of the mass of the moon, the mass of the earth, and inversely proportional to how far it is from the center of the moon to the center of the earth. And by the way, I want to go back and show you that diagram. And notice here on the diagram that r is the distance from the center of one mass to the center of the other mass. It's not just from the edge to the edge, it's from the center to the center. Okay. Now, if, and I'm going to go a little off script here, and then we can go back to your notes. If I claim that the cost is proportional to the number of liters, then that means I'm claiming that when we plot the data from an experiment here, you will get a straight line that goes through the origin. Are you with me? And that I can turn this proportionality statement into an equation if I knew the slope of the line. Because y equals, not proportional to, y equals slope times x. Well, if the slope is determined to be $1.8 per liter, then my equation is this. Would you agree? Okay. Isaac Newton is not making a claim about number of liters and cost to fill a tank. Isaac Newton is making a claim about force due to gravity. This is like that. This whole thing is like n. So what he is claiming is if you make a graph with mm over r squared on the horizontal axis and the force of gravity on the vertical axis, you'll get a straight line, and the slope of that line turns this proportionality statement at the top of the screen into an equation which we can use in the real world to calculate answers to problems. So how do you do that? Think about that. What we are talking about doing is on Earth, in a room, putting masses beside themselves, measuring the masses, which is pretty easy to do, put them on a scale, but then measuring the force of gravity between them. And I've already kind of alluded to how this is done. In Physics 30, we will deal with this in a lot more detail. But it's done using what's called a torsion balance. And it is literally two very, very massive spheres connected and balanced by a wire. The front sphere looks bigger because it's closer to your eyes. That's what we're talking about here. And then what Cavendish does is he takes another sphere that's on a rod and he brings it close to this sphere, and what he discovers is this twists. As I said, if you get a chance to see this in university, it's spooky. Like you pick this thing up and it's heavy. Okay, you pick it up and you hold it there, and as soon as it's close enough, the whole thing starts to swing towards it. This is M1, you can measure it. This is M2, you can measure it. This distance is R, not necessarily an easy thing to measure, but you can measure the distance between the surfaces of the spheres and add the two radii. He determines the force, and we don't need to get into really all the details here, but he determines the force based on how much this thing spins or rotates. And you can think of it this way. I can, without this sphere in the mix, this is a vast oversimplification. I can apply a spring scale to this bottom sphere and pull it with 1 Newton and observe the angle it twists at. The wire has a certain tension to it, and I can record that. And then I can apply a spring scale and pull it with a force of 2 newtons and see how much it twists, and 3 and 4. And then I will have a table of values that relates the angle that it twists to the force. And then when I do the experiment, when I put this mass on here and I measure, the angle of rotation, I can figure out the force. So this is what's measured. He measures this. Measures the force due to gravity. He measures M1. He measures M2. He measures R. These are all measured. Still with me? It's a long, complicated process. I'm going to go back to this. If Newton is right, then a graph with this on the x-axis and this on the y-axis should be a straight line. Well, Cavendish has this big table with all these numbers in it now from his experiment, and I wouldn't be telling you all of this unless he got a straight line. So the fact that he gets a straight line means Newton was right. That's correct, which means that's correct. and Cavendish determines the slope of the line, just like you would for the slope of the line in your graph. That's why we did that lab just before we did this. How do you find the slope? You pick 2 points, and it turns out the slope of this line, when you do this experiment using any masses anywhere in the universe, we can't prove that, but you'll have to trust me on that, you get a slope of 6.67 times 10 to the negative 11. Now, if you look at the units here, your rise will be in newtons, your run will be in the units of this, which are kilograms times kilograms over meters times meters. When you take newtons divided by kilograms squared per meter squared, you get this set of units for that constant. Nate, stay with us, please. So Cavendish determined the value of the slope to be that. What that means, everybody, is that this, which was Newton's hypothesis, becomes this, which Cavendish proved, and we have a formula we can use to make predictions about the real world, about what the force of gravity between myself and the moon would be, or what the force of gravity is between the moon and the earth, or between the earth and the sun. Take a look at your formula sheet, please. Under dynamics, you will find Newton's universal law of gravitation. That's what this is called. This is called Newton's universal law of gravitation. It is believed that everywhere in the universe that formula is valid between any 2 masses. And so far there's no reason to doubt it, even though this equation is hundreds of years old. The gravitational constant has a value of 6.67 times 10 to the negative 11. And again, the units are Newton meters squared per kilogram squared. There's no way we're going to finish this entire lesson today, which is why I started off by saying your unit exam is tentatively scheduled for Tuesday of next week. It's going to be Wednesday of next week. Okay? We're going to break this down into a couple of days. So we're going to do a couple of examples together here today using that formula, and then we'll finish off the lesson tomorrow. Determine the gravitational force of attraction between a 65 kilogram person and the Earth using Newton's universal law of gravitation. Don't worry about the second sentence yet. So, how are we going to do that? The force due to gravity is G times the mass of the person times the mass of the Earth over the distance between their centers squared. Okay, well, the force of gravity is G, which is 6.67 times 10 to the negative 11. And just for today, we're going to make sure we put the units in. This is Newton meters squared per kilogram squared times the mass of the person, which is 65 kilograms, times the mass of the Earth. Well, you're not expected to memorize the mass of the Earth, but it is on your formula sheet if you ever need to use it. And it's on the side with your constants. There it is. Mass of the Earth is 5.97 times 10 to the 24 kilograms. You might wonder how we know that. We know it because of Newton's universal law of gravitation. And tomorrow I'll start the lesson by talking about how we figured out what the mass of the Earth was. So when Cavendish did his experiment, a result is the determination of the mass of the Earth. But anyway, we know the mass is 5.97 multiplied by 10 to the 24 kilograms. If you take a look so far at what I have written here, On the top, I have kilograms times kilograms. And then I also have in the unit combination for G, kilograms squared. By the way, this is capital G. So what I'm getting at is these kilograms are going to cancel. And then on the bottom, we have to put the distance between the person, between the center of the person and the center of the Earth. Well, if I draw the Earth, here's the Earth. It's not a perfect sphere, but it's pretty close. It's called a spheroid, and it's oblate, and it's flattened at the poles, and it's a little wider at the equator. But it's pretty darn close to a circle. If you take a look at the picture of the Earth from outer space, you'd be hard-pressed to see that it's not perfectly circular. Okay. So there's the Earth. The Earth doesn't have a crease at the top. It doesn't have a hole. It's a sphere. And here's the person. I hope everybody would agree that this is nowhere near drawn to scale. Right? If I were to draw this to scale, that's not drawn to scale. Have you ever seen a picture of the Earth from outer space? Can you even see the mountains? They say, and I've never checked this out, that if you took the Earth and you shrunk it down to the size of a billiard ball, that's how smooth it would be. You wouldn't even notice the mountains. That's how big the Earth is. These huge mountains are nothing compared to the size of the Earth. So really, the center of the person is right there. It's right on the surface of the Earth, relatively speaking. The center of the Earth is right here. So what is the distance between the center of the person and the center of the Earth? What is the distance between these 2 points? What's the radius of the Earth? There's no space between me and the Earth, but there is a distance from the center of my mass to the center of the Earth, which is essentially the radius of the Earth. So in this particular case, this distance is actually the radius of the Earth. And this, I suppose, is some alien in orbit. So we're going to put in the radius of the Earth. Well, go to your formula sheet. The radius of the Earth is 6.37 times 10 to the 6 meters. That was known, ancient Greeks figured out what that was by looking at lengths of shadows and heights of towers and things like that. It's not a difficult mathematical problem. So we can put that in, 6.37 multiplied by 10 to the 6 meters. Look at how I write squared. I put that whole thing in brackets. I don't just square the meters, I square the whole thing. And I want you to notice that on the bottom of this you will have meters times meters, which is meters squared, and we have meters squared on the top as well. We're going to get newtons. Now comes the time to calculate what this is. 6.67 multiplied by 10 to the negative 11 times 65 kilograms times the mass of the Earth. You're entering this in one shot, and you do not need brackets anywhere in your calculator. And you always are using your exponential notation button. So I want to pause for a second here. If you enter 6.67 times 10 to the negative 11 this way, then stop it. Don't do that anymore. I do not want you doing that. It causes problems with the math. And I don't know if that's come up yet. I don't think it has. Have we talked about that yet? No. So don't do that. Use this EE, which is exponential. It stands for exponential notation. And when I enter 6.67 multiplied by 10 to the negative 11, it knows that E is times 10 raised to whatever number is there. And it walks those things together. Okay, times 65 times the mass of the Earth divided by 6.37 times 10 to the 6 squared. And that's exactly how it should be entered, and that's exactly how I want you entering it. And I want to make sure everybody does this on your calculator and make sure that everybody gets 637.87 something. So the force due to gravity between the Earth and the person is 637.87 newtons. Well, we've already talked about the force of gravity this year. That's called the weight of the person. So when I say this person's force of gravity between the person and the Earth is 638 newtons, I'm saying they're being pulled towards the surface of the Earth with 638 newtons of force. By the way, there's all kinds of things we could discuss here. The Earth is being pulled towards them with 638 newtons of force. Nothing special about them being on the Earth. The Earth is on them. They're on each other. They're making contact with each other. So I'm going to pause there. Does anybody have any questions with that calculation? This is the weight of the person. Well, hang on. Wait a minute. Wait a minute. Oh, come on. Nothing? It's too late, Alex. My feelings are already crushed. We've been taught that you can calculate the weight of a person using F equals mg. Little g, not big G. So, what do we get? Let's take 65 kilograms multiplied by little g, which is 9.81 newtons per kilogram. $637.65. And I think what we're going to do here is talk about this for a minute, do one last example, and then I'll just give you a couple to try. Why are these two not the same? I want you to think about that. Why, if the weight of the person according to Newton's universal law of gravitation is 637.87, and according to what we've learned previous in this unit is 637.65, why are we not getting the same answer? And there are a couple of reasons. Alex, do you know what one of the reasons is? So there's an issue of rounding. You're absolutely right. In fact, if you look up Newton's universal law of gravitation, capital G, even with that, it's not exactly 6.67. Not only are we rounding some of the answers we get, the numbers we're using are not exact. And it's not exactly 9.81. But there's another reason. And it's a more important reason. I'm not diminishing your answer. Your answer is absolutely right. There's a rounding conflict here. Yep. It turns out there's no difference. Towards the surface is towards the center. That's not actually it. And I don't know if anybody's going to get this Very few people do. We can use 9.81 where? I've mentioned this before. Yeah. Not necessarily at sea level, but what I'm going to say, Kai, is we use 9.81 here in Alberta. We're pretty close to sea level. We're not far off. But as you go further, how many of you remember me mentioning that if you go to Mexico City, that's quite a high altitude, there's less gravity. So the reason for it having less gravity in Mexico City is R is bigger. Mexico City is further from the center of the Earth than we are, so things weigh less. So I don't know for a fact, but maybe in a physics textbook in a Mexico City high school, they might say little g is 9.79. I don't know. Be an interesting thing to look at. But when we use that 6.37 times 10 to the 6 meters, that's for an average distance from the center of the Earth. And we are getting, if you take a look at what we got a little bit less, which means we're a little bit higher than the average radius. Okay. With that said, I'm going to jump ahead and we're going to do one more question. Mount Logan is in the Yukon and it's 5,959 meters above sea level and is the highest peak in Canada. So we assume that sea level, everybody, it represents the average radius. And I know that some of you might quibble with that because where the water is, you have mountains that are higher. So the average radius you would think is higher. But the Earth goes below the water in the oceans. So the average radius of the mass tends to be at sea level. So it says, what is the weight of a 55 kilogram person at the top of the mountain compared to at its base? You are going to have to do for me now 2 calculations. One of the calculations will be at sea level. And by the way, Kai, later on in the week, we're going to do a calculation of what our altitude above or below sea level is based on 9.81. And you'll see that it's not quite sea level. It's darned close, but it's not exact. You're going to have to do one calculation with that as a distance. Don't forget to square it. And this will be at the base of the mountain. And you're going to have to do another calculation with this as a distance. We're still going to have on the top capital G, 6.67 times 10 to the negative 11, times the mass. So we're still going to have capital G times 55 kilograms times the mass of the Earth and I'm really hoping you're okay with me just writing capital G. We know it's 6.67 times 10 to the negative 11. I don't need to write it down every time. I can just look at it on the formula sheet. And I'm also just writing the mass of the Earth. Rather than 5.97 times 10 to the 24. You can follow along with what I'm doing. Or if you have some confidence, you can just try it on your own. Some of you, I suspect, have already got the calculations done. I always recommend with this kind of stuff that since you have all those numbers, before you hit equals, take a look at it. You people with a TI-84 or a higher, you're at a disadvantage because things scroll off the screen. It's a real downside to that calculator. So there's my universal constant times the mass of the person times the mass of the Earth divided by that distance squared. So 539.73 newtons. That's at the base of Mount Logan. If I do the same thing at the top, I'm just going to repeat the calculation, but look how I have to enter this. I do need a set of brackets on the bottom because I'm going to add that 6.37 times 10 to the 6 plus the 59, and then square it. Did I get that number right? 5,959 meters? Is that what is in the question? So, doesn't matter the order I put these in. In fact, I'm going to go to a clean page here so you can't see which was which. This was at the top. Nope, this was at the base. This was at the top. It's about a Newton, which isn't a lot. I mean, you played around with spring scales, you know what a Newton is. It's not a lot of force. But, you know, technically, you want to lose weight? Climb a mountain. Now, you will lose weight because you will be further away from the center of the Earth. You'll also lose some weight because it's going to burn some calories going up the mountain. Okay. But when people say, oh, I'd like to lose some weight, what they really mean is they would like to lose some mass, right? I need to lose some kilograms. Okay. Get back to my fighting mass, high school mass. So objects weigh less the further away you are from the center of the Earth. That's the bottom line. I'm going to give you just a couple of these problems that I would like you to do as practice for tomorrow. Let's do, you can circle number 4. No, not yet. Circle number 7, 8, and 9, 7, 8, 9. Just 3 to do for tomorrow. 7 and 8 are very simple. I want you doing them using Newton's universal law of gravitation, not using mg. 7, 8, and 9. 7 and 8 are fairly basic. They're just like the ones we did. Number 9, you got to think about a little bit. And that's your assignment for tomorrow. Tomorrow we're going to finish off and get lots more practice with this stuff.